Hello and welcome to the first video of the FP1 chapter Transformations Using Matrices. Show that the identity matrix has no effect when multiplying matrix A. Quick starter question to review some of chapter 5's work which you need to have done before starting this chapter. So if you remember, the identity matrix is this one in a 2 by 2 matrix. We're going to multiply that by this one. And we can show it has no effect by going ahead and doing the multiplication. This times this is 2, plus 0 gives a 2. 1 times 7 plus 0 times minus 1 is a 7. 0 minus 4 is a minus 4. And finally, second row, second column, 0 take away 1 is a minus 1. And we can see that that's the same matrix as we had here. We'll be doing a bit of multiplying matrices in this chapter. So an overview, we're going to represent linear transformations with matrices here. Then in the next video, we've got reflections and rotations, then enlargements and stretches, and in the final video, we'll do these two together. So representing linear transformations. In GCSE, we did this by describing the effect that a transformation had on a shape. For example, if we had something like this, and then you transformed it, and it ended up something like this, then you would say, oh, it was a reflection in the y-axis. And that sort of description would be the way a question would tell you to do something. It would say, reflect in the y-axis, as the command in the question. But you don't need a whole shape to do that if you could do it with a general point. If you could see the effect using the general point xy with position vector xy, then you could define the transformation with the effect on that one point. And this is what we do with matrices, because we can use algebra to show how that point changes. So here, a bit of notation. This is saying the transformation S changes xy, the general point, or the position vector of the general point, into the point with position vector this, where the x has become x plus 3 and the y has become y minus 2. So this is a translation effect. Another example, the transformation T has the effect of changing the position vector of the point xy into the position vector 2x plus 3y squared and x plus 7. And this is not a very simple transformation, like this is a translation. I can't just say, oh, this is a, and then tell you something from your GCSE work, because this is quite a complicated expression for the x and an expression for the y that involves the x, but not the y. So you wouldn't be expected to know what this means in terms of a geometric change. And in fact, you wouldn't use either of these in most of this chapter, because what this chapter focuses on is something called linear transformations. And linear transformations are a very specific type of transformation that only use linear terms in x and y. Something like this, where your x changes into some number of x's plus some number of y's, and so does your y. And part of the reason for that is because this is such a useful form of a matrix applying to xy, because from our knowledge of matrix multiplication, you can find this just by using the matrix A, B, C, D, using the coefficients of these things here, because we know that this is how matrix multiplication works. If you apply this matrix onto xy, you have to do A times x plus B times y to get this element, and C times x plus D times y to get this element. So this is a very useful format because it comes from this. And actually, if you look into why we do matrix multiplication in the way we do it, a lot of the answers given suggest that it's because it gives this linearity here. And these are the only types of transformations that we'll be doing in this course. A final thing to say about this is that linear transformations always map the origin onto itself. if you have a 0 and a 0 here, there is no way you can get anything other than a 0, 0 out of this. Which is why the example we had on the previous screen, x plus 3, things like that, they are not linear transformations, because you can't get a constant term out of this. And an x plus 3, a translation, you know doesn't map the origin onto itself. A translation would move the origin as well as it would any other point. So whether you want to take that as part of the definition or if you want to take that as a direct consequence of this definition here, either way, this will be a true statement for all of the transformations that we look at. So using these ideas, let's have a look at a couple of examples. Identify the non-linear transformation out of these three, and create matrices to represent the two linear transformations. So we've got to find the one that's non-linear and then create matrices for the other two. Now this is quite an easy question because of the connection up here. If you've got a transformation given by this and you want to find the matrix that represents that transformation, literally all you're doing is taking the coefficients of these 4 bits and putting them into a matrix. So first of all, I've got a 5x here, so the 5 is relating to the A, so that goes in the top left of my matrix. And I don't have any y's, but that means it's a 0 for the B. It doesn't mean it's non-linear. So let me write this out as I do it. We can say 5, 0, and then the next one we've got 2x, so the 2 is the C, and minus 7y. 2 minus 7. And again, that's because we know that if I apply this on here, this is what I will get. I'll get 5x plus 0y, so that's 5x, and 2x minus 7y for the second element. So you don't need this part, it's not part of the question, but that's why this is the matrix that represents this transformation. The second one, just as straightforward, I can see that this is a linear transformation because I can do the same thing. Here we've got minus 3, 2, minus 1, minus 1. And that must mean that the last one is non-linear, and it is. Although it looks like it should be linear because it doesn't have any squareds or cubes or square roots or anything, but even so, I can't get a plus 3 constant out of this process. There is no number I can put into this matrix that will give me a plus 3 as a constant in either of these elements here. So because of the plus 3 and because of the minus 4, this is non-linear in terms of a transformation. And like I said before, this is representing a translation which does not keep the origin in the same place. Second and final example. The square S has coordinates these. Find the vertices of the image of S under the transformation given by the matrix M. Sketch S and its image on a coordinate grid. Okay, to help us do this, I'm going to sketch S on the coordinate grid first, and I'm not going to sketch it so much as accurately plot it. So we've got 1, 1, 3, 1, 3, 3, and 1, 3. So this is my square that I've got here, which we've called S. Now we're going to apply the transformation M. I haven't explicitly explained how to do this, but I hope it's implicit from this statement here. We've got M, the matrix, the transformation, and we've got the coordinates given in 4 different points here, and we're going to do the multiplication. It's very important that the transformation matrix stays on the left of this, the coordinates on the right. Remember, the order of matrix multiplication is very important. But I'm basically just going to do 4 lots of multiplication. So we've got the matrix, minus 1, 2, 2, 1. And we are applying this onto a set of coordinates, but not the general point xy. I've got an actual coordinate here, 1, 1. So the coordinate 1, 1 gives me the position vector 1, 1. And then I go ahead and do this multiplication. So we've got minus 1 plus 2 is a 1. And of course there's only one column here, so that's that finished for the first row here. Second row, 2 plus 1, that's a 3. So my 1, 1 coordinate has transformed to 1, 3, which is a little bit of a shame because I already have a coordinate there, so it's going to overlap slightly. But it's this point here that has changed, transformed to the point in green. And then we go again with the next coordinate. So now I need to apply this transformation matrix to the coordinate 3, 1. Minus 3 plus 2 is a minus 1. And then we've got 6 plus 1, which is 7. Minus 1, 7 is way up here. And that is this coordinate transformed up here. Third coordinate is 3, 3 in position vector form. Apply the matrix. Minus 3 plus 6 gives me a 3, and 6 plus 3 gives me a 9. So we've got 3, 9 way up here. And that's this coordinate transforming up to this one. So it's not a very standard transformation. You can see here it's not just a simple enlargement or a simple rotation, it's a bit of a combination of the two. So here we go, minus 1, 2, 2, 1 applied to the final coordinate 1, 3 is going to give minus 1 plus 6 is 5, and 2 plus 3, which is also 5. 5, 5 puts the final coordinate exactly where we expected it. So you can see the square has enlarged and rotated in one big transformation. We could call this S prime, the image of S. And that's fairly straightforward, I hope. If it might seem a little bit long, then I can show you a method to shorten this process. And that's possible because we've got this matrix applying to 4 sets of coordinates, but we don't have to do them one by one. We can combine them into a 2 by 4 matrix. The first coordinate in the first column, the second coordinate in the second column, the third coordinate in the third column, and of course the fourth coordinate in the fourth column. And so long as you keep your transformation matrix on the left and your coordinates on the right, you can do all of this in one big go. It doesn't give you any different answers, obviously, you get all the same answers, but it saves you writing out the process 4 times. So you get minus 1 plus 2, of course, is a 1. Minus 3 plus 2 is a minus 1, and you can see a slight difference. I'm doing all the x coordinates first, and then all the y coordinates, but that's okay. Minus 3 plus 6 is a 3. Minus 1 plus 6 is a 5. Then onto the second row. 2 plus 1, 3. 6 plus 1, 7. 6 plus 3, 9. And 2 plus 3, 5. And then you just read off the coordinates in columns again. 1, 3 in red. Minus 1, 7. 3, 9. And 5, 5. So you can do it in one big go by combining your coordinate columns, your position vectors, into a matrix and making sure that the transformation matrix is still on the left. And that will give you the set of coordinates for each of your 4 image points. So I hope that will save you a little bit of time in the questions, which you can practice in exercise 6A. And maybe I'll see you for rotations and reflections.